So the first formalised method of solving a system of equations this way is called Gaussian elimination, named after Carl Friedrich Gauss. So far we've seen that you can transform a system of linear equations into matrix form, and you could solve it by using the inverse, but if the system was upper triangular, then you can do it by back substitution. And we just saw a very simple example of making it the system upper triangular using subtracting multiples of one row from another. Okay, so Gaussian elimination, we start with this linear system, and the first thing is to get rid of these lower triangular block. The x's stay the same, but of course the b's will change because we're adding multiples of one row to another. And if you think about, why are we doing operations on rows rather than columns? If we did operations on columns, it would change the x variables. So it would be harder to work out what the answer was if we did it that way. That's why we're doing operations on rows, because they keep the x's the same. And so if x1, x2, x3 is the solution of this system, it's also a solution of this system. Okay, so as a notational thing, we tend to just write down the coefficients. You don't kind of need to write the x's, and so it's often written as a kind of augmented matrix, and we just put a line down there for convenience, because the operations we're going to do are all on the rows, including the b's as part of the rows. And in fact, you don't really need to put brackets around it, you just need to write a neat table. And so for a 3x3 system, these red stars are the targets that we want to get rid of. And rather than a kind of ad hoc way of solving a system of equations, this is systematic in the order that we get rid of them. So first of all, we use the first row to get rid of that number and make that 0. And then we use the first row to get rid of that number. And the point is it changes the other numbers, but we want to just get a 0 there. We've got a 0 there, and then actually, of course, the point is that once we've got a row that's got a 0 in the first column, then when we operate it on the other rows, it will still have a 0 in the first column. So we've kind of got this last column sorted out. And so the next target is to get rid of this number here, and we can do that by subtracting a multiple of this row from this row to get rid of that number, and of course changing these numbers. Obviously we don't use the first row again because that would change to 0. And then we've got an upper triangular matrix. Let's look at an example. Here's a system. Hopefully it's non-singular, and it's kind of interesting that without working out determinant, there's a point at which Gaussian elimination tells you that if your matrix is singular. So it's the 2, the 1 and the 8 that we're trying to make into 0, but in particular first we get rid of the 2 and we get rid of the 1. So writing it as an augmented matrix, just sort of slightly less decorated, our first operation is row 2 becomes row 2 minus twice row 1. And so it is typically the way that we do it's the row take away some multiple of the other rows. And although of course you can make the arithmetic easier sometimes by making a multiple of the second row first, just to keep whole numbers, but formally Gaussian elimination, just subtract some multiple of the row above. So so doing that gets rid of this. That's why we came up with a number 2, and then it just changes the other numbers in the same way. Just do that to the row. Next we're going to get rid of this number, and to do that, let me just think, I'm going to subtract row 1 from row 3. So row 3 becomes row 3 minus row 1. It's a very good idea when you're doing this to write down what the operation you did. Even though it kind of might be obvious, it's very easy to make a mistake somewhere in the arithmetic. So it's handy to have a kind of audit trail of what you thought you did, and then you can check it. Okay, so now I've got those two zeros, and I've got the first column sorted out. And my next target is to get rid of that 6. And I'm going to do that by adding 3 times this row. So I'm using the second row because it doesn't interfere with the 0 I've already got. And that makes that 0, of course, changes the others. So for example, -2 plus 3 times -4. So -2 minus 12 is -14, and so on. Now at this point we can use back substitution. So the last row says -14x3 is equal to -14. So x3 is 1. And that's easy. You know x3 is 1. So -2x2 -4 is -6. So of course x2 is 1 as well, because -2 minus 4 is -6. And then knowing that these are both 1, of course, we're thinking 6 minus 2 minus 3, that's 1 as well. So the solution we can actually see is 1, 1, 1, but I got that by back substitution. So if you had a 4 by 4 matrix, the procedure is the same. It's just more work. That our first step is to get rid of the numbers below the first column. It doesn't matter what order you write equations in, they're still the same equations. Of course, it's a different matrix. And just in case you're wondering at this stage, if that number happened to be 0, then, I mean, if all the numbers in the first column were 0, the matrix would be singular. But if you're trying to use a 0 for that number, it doesn't work. So you just swap the equations so that you don't have a 0 in that first position. Anyway, using that non-zero, we get rid of the numbers below it and make them 0 by subtracting multiples of the first row. Then we've got zeros in that column. Now our next target is this number. Sorry, the next target, I'm going to use this number here, the red star, to get rid of these two numbers. So I subtract multiples of the second row from the third row to get a 0 there, and then I subtract another multiple of the second row from the fourth row, and now I've got zeros underneath the diagonal. So keep an eye on the diagonal there. It's the numbers below the diagonal each point that I'm getting rid of. And then my next target is this number, and I'm going to use the third row to get rid of that. Now I've got an upper triangular matrix. And I can back substitute to solve for x1, x2, and so on, starting with x4.